Today I'd like to discuss filtering and the effects of filtering on your bit error rate. We are going to start out by doing a very brief review of filters, very basic filtering concepts, and then we're going to build up to the issue of intersymbol interference, and in particular intersymbol interference that arises due to filtering and bandwidth issues. And following that, we'll be talking about how we can use pulse shaping to overcome some of these deficiencies. The motivation behind this section of the course today is to explain why we use pulse shaping and how it's good for dense wavelength packing. After we've gotten through that discussion, we'll talk briefly about how you would simulate these filters, and especially the noise in the presence of these filters. But it is some simulation methods, very standard, but we'll just formalize them a little. And then I want to talk about Monte Carlo techniques, about how we run a Monte Carlo simulation and how we can judge how well our Monte Carlo simulation is doing. I'm going to add a new paper to the website this afternoon, which discusses these Monte Carlo techniques, an old classic paper. And then the last topic today is going to be a paper by Windsor, which is very much in the same spirit of the homework problem that you'll be doing. He examines these filtering effects, and he explains the simulation method he used, and you'll see that your simulator you'll be using for the homework could be used to recreate the results in this paper. They're very similar, and so it's a very good example of how we can turn to numerical simulation to answer some questions for us. So, as I said, we're going to be going over a brief review of filtering. So we'll start with the most basic concepts. And of course, first of all, there's the ideal low-pass filter. So we have here the frequency response, just the amplitude of the frequency response. We assume it has zero phase response. And low-pass filter centered on DC has a certain bandwidth indicated here by FU for the upper frequency. The impulse response is the Fourier transform of this rectangle, which of course gives a sinc function. We could have also an ideal bandpass filter. They're called ideal filters because they're perfectly square, and they may not be realizable, but they're used as good approximations for certain situations. I want to point out something directly coming from Fourier analysis. Fourier analysis says, and the examples we have here are a triangular function and its Fourier transform, which is the sinc squared function. Here we have the sinc squared function in the time domain at the top, and in the bottom, on the right, we have the Fourier transform of this, which is a triangle. And by duality, we know that if we instead started out with the triangle in the time domain, in the frequency domain, we would have the sinc squared function. And so it is not a coincidence that in this example, in one domain, we have a function with infinite support, and in the transform domain, we have a function with finite support. For instance, when we have the sinc function in the time domain, it has infinite time duration, whereas in the frequency domain, it has a finite bandwidth. Of course, by duality, if we did the opposite, in the time domain, we have a time-limited signal, but we have infinite frequency terms in the frequency domain. And this is a general result from Fourier analysis, that one cannot have at the same time a time-limited signal and a band-limited signal. Okay, so we live in the real world, which means that a signal is limited in time. I don't go to the lab and wait for infinity of time to generate my pulse. No, I'm there for a while, and the signal is definitely time limited. So that means it cannot be bandwidth limited. It has infinite bandwidth. Of course, in reality, none of my measurement equipment have infinite bandwidth, which means that anything I measure is going to have finite bandwidth. So there's this sort of inconturnable result from the mathematics saying that if all my signals that I have in the lab are going to be of infinite bandwidth. And that's just not quite right. Well, even if mathematically they are of infinite bandwidth, practically the frequency response becomes very small for large bandwidth. And I want to have some way of quantifying this fact that somehow the bandwidth is less wide if I have a faster spectral roll-off. And for that reason, we talk about bandwidth of signals even if they're theoretically have infinite bandwidth. And so that comes to the question of how do we quantify bandwidth? Because there's no strict mathematical definition. The strict mathematical definition would give us infinite bandwidth. But of course there are many reasons why we want to find out a way to quantify bandwidth in a reasonable way. And the biggest reason is because it's really relative bandwidths that are important. We intuitively know that if we have a signal that's very wide in bandwidth, like let's look at the lower, the B case here, where X of F is the spectrum of the input signal, and it's very, very wide, and we look on the right in the B case, and we have a channel that's fairly narrow. Well, we know something's going to go terribly wrong when we try to put this input signal through that narrowband channel. If we're in the upper case, in part A at the top, where the input spectrum is fairly narrow relative to the response of the channel, we think that our signal is going to get through without much distortion. So we know this intuitively. We look at it by eye, but we really need a way to quantify each of these signals, which each of the channels, each of the signals has infinite bandwidth if we go by a strict definition. But of course, practically there's some finite bandwidth we can use. So there's several definitions for bandwidth that are available. I'm going to focus just on two of them that we see the most often, which is the 3 dB or half power bandwidth and the noise equivalent bandwidth. I think I also use null to null in some of my examples. But in any case, very simple definitions. The 3 dB bandwidth, also known as the full width half maximum bandwidth. We take the frequency response, we look at the peak of the peak frequency response, and then we follow the frequency response down to where it first reaches half of the initial value. At that point, we look down at what bandwidth has occurred, and we call that the bandwidth of the signal. So this is the 3 dB bandwidth of the signal. Now a second definition, and one that we need when we're modeling noise, noise effects, is something called the noise equivalent bandwidth. So in this case, on the left in blue, we have an arbitrary, I think this is obviously a sinc function, but just say an arbitrary frequency response with infinite frequency support. If we take the area under the curve, and then, we can do this numerically if we have to. We can do it analytically if we have a good expression for it. But the important thing is that we form afterwards a rectangle with the same height as the maximum of the original frequency response. So the original frequency response has a maximum of A, so we fix our rectangular frequency response to a height of A, and we define the bandwidth B to be that bandwidth that has equal area, gives equal area to the rectangular response that we would get under the area of the curve and the original response. Okay, so that's one definition of bandwidth. And why do we call it the noise equivalent bandwidth? That's because we assume that we're dealing with additive white Gaussian noise, which is flat in the spectral domain and has infinite frequency support. So suppose we took this additive white Gaussian noise signal and we filtered it with the frequency response in blue. Well, then the power of the noise that would be emitted would be the equivalent as if we had used a rectangular filter with bandwidth B, well, two small b's here. That would be the noise power that was let in by this filter. So if we want to simply know what is the effect of a wideband additive white Gaussian noise being filtered by this filter, we could say it's the same as if we had used a rectangular filter. As far as the noise is concerned, this could simplify our analysis, but of course the signal, perhaps the effects will be different. But as a way of characterizing a filter, this is a very useful characterization of bandwidth. So here's a graphic for the sinc squared function, and this shows how different the results are for what we would call the bandwidth of this signal, just based on definition. So different definitions give different values for bandwidth. It's important simply to understand when you read what the bandwidth is, what it's referring to, and how it may be useful to use. 3 dB bandwidth may be a good figure of merit for determining how much distortion will be introduced to a signal. The noise equivalent bandwidth will be a good tool for determining how much noise is getting into your system. If we move on just on this brief review of filters, one other concept which is very important is the causality effect. A definition of a causal filter. A causal filter is a filter whose output is only a function of prior inputs. That is, the output is not a function of the future. That means we cannot build a system that predicts the future. Of course, all practical filters are causal filters. However, in the mathematical domain, we will often play with, design, exploit, take advantage of non-causal filters. But you have to always keep in mind that when it's time to build these filters, that there's some accommodation has to be made to make them into practical filters. And then again, just to see the impact of what a causal filter is, let's look at the impulse response, small h of t, of a system. We have the output y of t is equal to the convolution of the impulse response h with the input signal x. We have the integral definition of a convolution. And then finally, to the right, we have changed the limits of the integration from minus infinity to infinity to instead be from minus infinity to t, the current time. So the output y of t can only be a function of the signal x of u here inside of the integration from the negative infinite time until the present point. That means that we have assumed that h of t, the impulse response, is 0 for all negative values of the argument. Causal filter is a filter whose values are 0 for negative values of the argument. For instance, let's look at the low-pass filter. If we look at what is a causal version of a low-pass filter, not an ideal low-pass filter, but a filter that filters out high-frequency content. Well, one version would be an RC. This is a resistance capacitive circuit, an RC circuit, that forms a low-pass filter. And we can see that it has a frequency response that is 0 and then falls off exponentially. If we look at the frequency response for our ideal low-pass filter, it's the sinc function, and of course it has infinite time support. So this is a non-causal filter. Of course, the more high-frequency terms are introduced with the causal RC realization, and we would like to get something that approaches the ideal filter, cutting off more high-frequency components, if we could get an approximation to the ideal low-pass filter. So what we can do is to render the ideal low-pass filter causal. And in order to render the filter to be causal so that we can actually build it in the lab, is to first truncate the impulse response so that it is no longer infinite. And then we have to introduce a delay. There's a trade-off between how sharp is the cutoff in the low-pass filter in the frequency domain, depending on how much we truncate it. So if we let it go farther and farther, the impulse response wider in the time domain, of course we'll get a sharper cutoff in the frequency domain, but that will mean that we have to introduce more delay before we can take the output and use it. So there's a trade-off. But anyway, this is just to say that although ideal filters don't exist in reality, there are ways that we can approximately achieve it. And now I'd like to talk about intersimple interference, also known sometimes as the patterning effect. And in particular, I want to talk about how intersimple interference comes out of filtering effects. So we said that our channel is practically always bandwidth limited. Any components that I use have a finite bandwidth. They'll only support signals over a finite bandwidth. And the signal, of course, is always time limited, so it's never bandwidth limited. That means that I'm always trying to force through a signal which is essentially of infinite bandwidth through a channel which is always of finite bandwidth, which means that I should, because of this, lead to pulse broadening. Of course, it's all a question of degree. To which degree will I get pulse broadening? First of all, I'm going to show you why it is that this gives you pulse broadening, and then I'll try and show you how to quantify how much pulse broadening you get from this effect. So let's take a really simple example. In this example, I'm plotting here first the frequency domain, and in blue is my signal. So I have a signal with the bandwidth. I think I actually used the null-to-null bandwidth when I was doing the simulations. And I put this signal through a channel with rectangular frequency response. The bandwidth of the frequency response is 10 times the bandwidth of the signal. And this signal, you can see it's a sinc function, which means if I look in the time domain, in red I have the original rectangular pulse which is transmitted. It goes through this channel which has 10 times the ostensible bandwidth of my signal. And in blue we see the output of the filtering process, and we can see some small ringing at the edges of the signal. When the signal goes to 0, in fact it doesn't go to 0 at the output, there's some blue ringing around 0 that we can see. And this is sort of a stretching of the original pulse, so this time duration is greater. Now what happens is I try to squeeze this signal into a smaller channel. So now I'm going to show you simulations where I just put the signal through a channel with comparable bandwidth. Now when the two bandwidths are about equal, you can see that I have much more ringing coming out of the filter, and that now the time duration of the pulse is wider. There's ringing off in the 0. And of course if I try and make the bandwidth channel smaller, what I get is more spreading, in fact quite a bit more spreading in the time domain. And if I try to get a very ridiculously small channel that is 1/10 the bandwidth of the original signal, I have immense amount of spreading. So this is why channel effects alone can lead to dispersion of the original pulse, so that the pulse is no longer confined to a limited time duration. And of course this would be fine if I sent bits in isolation, but of course I send a train of bits when I communicate, which means that one pulse will not have finished due to this spreading in the time domain before the next bit is transmitted. And so what is received at the receiver is the accumulation of all of these pulses, some overlapping. And so on the far right, on the bottom, we see the received signal, which looks very different from the rectangular pulses which were sent on the left. And in fact, if we set a threshold at the midpoint of the 0 and 1 levels on the received signal, we can see that sometimes we could make an error. If you notice, the dashed lines indicate the sampling point of the receiver. So at the sampling point, which would normally be at the widest point of the eye opening, we could, even though we had a 0, mistake it for a 1 if the spreading was severe enough. So this is what we call the intersymbol interference effect. And again, as we saw in the example, the level of the intersymbol interference is directly related to the relative bandwidth of the signal in the channel. I just wanted to mention that, of course, we also have in optical communications other sources of pulse spreading. We can get intersymbol interference from dispersion in transmitting signals, pulses over an optical fiber. Same effect on bit error rate. However, I'm going to be talking about ways of combating intersymbol interference, how to avoid intersymbol interference. And of course, these methods are for intersymbol interference originating from filtering effects. And they wouldn't, if we have other methods of combating chromatic dispersion in a fiber. But now I'm talking about filtering effects. So we know that this sort of intrinsic problem with transmitting through bandwidth-limited channels is the possibility that intersymbol interference will raise its ugly head. And so we want to come out with ways of avoiding it. Why is intersymbol interference so bad? So let's look at a typical bit error rate curve, which we see illustrated here. And it has here the typical waterfall shape. And if I had a really bad channel, I would maybe be on a noisy channel, a channel with a lot of noise in it. I would maybe be on the dotted line instead of the solid line. And if I wanted to get back, well, this is not quite the right way of saying it, but if I had too much noise in my system, I could always raise the power of my signal to bring my signal-to-noise ratio back in line to achieve whatever bit error rate I wanted to, so that you can overcome noise problems with signal power. Of course, there's always a limit to that, getting to nonlinear effects, etc. But just in a simple system, too much noise, I add more power to the signal. However, what happens with ISI is we create something called a bit error rate floor. I might have the waterfall shape, but then I lose it at some point. And even if I add more signal-to-noise ratio, if the noise is fixed by adding more signal power, I cannot infinitely climb down the bit error rate value just by increasing SNR, which is what I can do for the waterfall curve. I can always get better performance, go down to any bit error rate I want by simply increasing the signal-to-noise ratio. But with intersymbol interference, of course, I can't. And the reason I can't is because when I raise the signal power, I'm also raising the power of the interference. Here you can see it. That if I raise the level of the 1, it might help me against additive white Gaussian noise, but I'm just going to, all the interference that stems from the spread pulse will grow just as much as my desired peak. So that's why it's really important to avoid intersymbol interference due to filtering. Filtering we have to do. We have to filter. First of all, our channel filters it because our channel has finite bandwidth. But even at the receiver, we filter. And some classic results from communications theory is that if we have an additive white Gaussian noise channel, then the best strategy for detecting binary bits, for instance, is to use what we call a sampling receiver. So here we have a block diagram of a sampling receiver where we have the signal coming in. It's being added to that is the white Gaussian noise. That's why we call it an additive white Gaussian noise channel. RFT is the received signal. And in the blue box is my sampling receiver. And the first thing my receiver does is filter. And I filter because it's a very broadband noise, and I want to diminish the noise as much as possible. And after the filter, I get a continuous time signal, which I sample, and I sample at the bit rate. The sample that comes out we call our decision statistic, and we compare the decision statistic with the threshold to ultimately come up with our bit decision, our bit estimate. So if we look at the theory from communications theory, what filter should we use? And theory tells us that in order to maximize the signal-to-noise ratio in the decision statistic, we should use a matched filter. Matched filter means that the impulse response of the filter is matched to the shape of the impulse into the received signal R of t. So H of t is actually equal to the impulse response is equal to the conjugate of the Fourier transform of the received signal. Okay, so in order to maximize signal-to-noise ratio, the filter shape that I should use should look just like the received signal pulse shape. Also, if I want to maximize the a posteriori probability of the estimated data, then theory tells me I should use a matched filter. So for many different ways of looking at the problem, the best strategy is to use a filter matched to the incoming signal. That means that I've sort of traded off, how to get the most of the signal information and reject as much of the noise interfering with that information as much as possible when the noise is additive white Gaussian noise. And according to theory, pulse shape doesn't matter. Whatever shape RFT has, as long as my filter is matched to it, as long as I use a matched filter, I will get all the good results I'm looking for. But of course, all that theory uses some simplifying assumptions. And one of the simplifying assumptions is that the there is no intersymbol interference present. Pulse shape, in fact, is used to ensure that we really don't have any ISI present, that's true. So when I developed equations for the bit error rate, I developed those equations based on an additive white Gaussian noise assumption, based on the sampling receiver. These estimates of the bit error rate are only accurate if there is no intersymbol interference present. And then I'll get the theory will give me those nice waterfall shapes. So if I want to be able to use my theoretical results, I've got to be working in a regime which is ISI. If I want to avoid getting a bit error rate flora, I want to be working in a regime that doesn't have ISI. So although theoretically I can use any pulse shape I want, in fact, if I want to avoid ISI, there are some pulse shapes that will help me do that when I'm using non-ideal components. Okay, so I'm going to talk a bit now about how I would simulate these systems, and what does a system look like which has some pulse shaping in it and then has transmission over a channel and reception in a sampling receiver. So this would be a typical diagram of how you would simulate such a system. You would put in Dirac functions, these are just your bits, 0 and 1 bits, would go into a transmitting filter, and the role of this filter is to shape the pulse to the desired shape. So we would choose the impulse response of this filter to be equal to the pulse shape that we want to achieve. After the transmission of the pulse train, it would go through a channel which introduces noise, go into a receiver that filters in some way or other, a sampling receiver, and then it would sample, it would go into the threshold decision box. So if we wanted to maximize the SNR, we wanted to come up with the maximum a posteriori estimate of the true bit, we would use the strategy of having our received filter be matched to the received signal. So it's not matched to the transmitted signal, it's matched to the received signal. And the received signal is the convolution of the transmitted signal and the channel impulse response. Or if we look in the frequency domain, we would say that the transfer function of the received filter should be equal to the conjugate of the product of the transmit pulse frequency response times the channel frequency response. So instead of building all these different filters, whether we're doing simulation or analysis, it's often useful to deal with an equivalent system where we group together all of these filters into one equivalent filter. And so the equivalent filter is just the cascade of the 3 filters together. And then we would add our noise after this point. And this is one of the most critical points that people can make a mistake in when simulating system, and that is how to add the noise. If I were simulating the system on the top row, I would use the AWGN command, for instance, in MATLAB, and add a wideband noise. I add wideband noise because that's in the channel what the noise would be well modeled at, but in knowing always that the receiving filter is going to filter this noise. Now, when I've tried to come up with a more convenient way of modeling, it's important that in the second case in the bottom, that when I add the noise, I no longer add broadband noise. What I should now use is an equivalent bandwidth limited noise to accurately assess what's going on in the system. We'll talk a little bit about how you would calculate what noise level you should use post-filtering. Now we want to get into what would be a good choice of pulse shape. If in theory I can use any pulse shape I want, in practice I'm going to use a shape that is convenient for me or has some good properties for me. And one of the definitions of what would be a good property in a sampling receiver is that the pulse should be 0 at all sampling times except 0. I'm not talking about intersymbol interference now. I'm just talking about sending a pulse train. If I send a pulse train, I want to know that when I sample and I want to look at a particular pulse, I'm only going to get non-zero input from the pulse that I'm sampling at instant, and that all the other contributions from other pulses, previous, later, they all contribute 0, and they're not part of my decision statistic. So that is the definition of what we call a Nyquist pulse. Normally, if we had a pulse that was greater duration than the time of 1 bit, we would be worried that even without the filtering effect, we would indeed be creating intersymbol interference. But if we follow this definition and only consider Nyquist pulses, then I will not get any intersymbol interference, even though the pulse has maybe infinite duration, but at the very least is not confined to 1 bit time. So there is overlapping of pulses, not due to any filtering effects now. I have overlapping of pulses because that's how I design my pulses. But the overlapping is controlled. It's controlled in such a way that I choose pulses that pass at 0 every time we go through the sampling time, except of course for the main lobe of the bit. So there are many examples of Nyquist pulses, and of course the most obvious example is an RZ pulse, a rectangular pulse. A rectangular pulse is 0 outside the bit interval, so of course at all the other sampling times it is also 0. The sync function is a function that also goes through 0 periodically at every bit interval. So that would be a valid Nyquist pulse. There's also a pulse called a raised cosine pulse, which is one that is commonly used in the laboratory because it has many nice features, and it is, let's say for now, another example of a Nyquist pulse. I think you've probably heard of a root raised cosine pulse, and that's not actually a Nyquist pulse. It's an abuse of the vocabulary a little, but it's related to the raised cosine pulse, which is a valid Nyquist pulse. So let me just use the term about the ideal Nyquist pulse, which we hear sometimes. And the ideal Nyquist pulse has the form of a sync function in the time domain. And in the frequency domain, it has a rectangular frequency response. Signal in the time domain is on the right. It's a signal which takes the form of a sync. So it is every signal sent, every bit sent actually has infinite time duration. You have to be in the lab a long time for this one. And however, every time sampling interval, it will pass by 0. And if we look in the frequency domain, it has a very, very small bandwidth. In fact, it's called ideal because among all of the Nyquist pulses, it has the smallest bandwidth. It is the most spectrally efficient of all Nyquist pulses. So it has some other bad qualities, but one good quality it has is that it's very spectrally efficient, and that's why it has gained the name of the ideal Nyquist pulse. I talked about spectral efficiency, and of course spectral efficiency is the ratio of the transmission rate divided by the bandwidth occupied in order to achieve that. So if I hold constant the transmission rate for all Nyquist pulses, their bandwidth is different, and this bandwidth for the ideal Nyquist pulse is the smallest one, and thus is the most spectrally efficient. So I said that we have a family of Nyquist pulses that we can use, and what do we want to achieve? Why do we have such a wide selection of pulses? Well, we want to trade off to try and get something that is bandwidth efficient, but can also help us avoid ISI due to filtering effects. And of course, bandwidth efficiency will do that. It'll help us avoid ISI. Something relatively easy to implement and something that's robust to timing errors. And I'll show you how these nice pulses can achieve them. So remember, pulses which are limited to TB, they're wide in bandwidth. If you have time limited, that means they're wide in bandwidth. And if I have a really wide bandwidth, I'm going to run into trouble with the intersymbol interference. So that's why I don't like to use the rectangular pulse if I have to, because that's more vulnerable to ISI just because it takes up a lot more bandwidth. If I use Nyquist pulses that have a time duration greater than TB, if I have no pulse spreading, then there's no ISI, since these Nyquist pulses pass to 0 the sampling time. And they can be narrow band. We saw that the ideal one is very narrow band, so ISI will be less likely because I'm taking up less space in the frequency domain. Historically, optical channels were very, very wideband, and that we didn't worry about these spectral efficiency. But now as we're going into more dense packing of spectrum, having spectrally efficient pulses is more important. And also, they can be more robust to timing errors if we do our choice correctly, which can also be very helpful in the system, and I'll show you about that trade-off. So let's look at the raised cosine. I have the definition here. These are programmed into MATLAB already. It's programmed into OptiSystem. But the important thing I just want to show you in these equations is there's a sinc function and there's a roll-off factor. And the roll-off factor is a factor that we can tweak in order to trade off different characteristics of this pulse in order to favor some characteristics over others. For instance, spectral efficiency, because we can see the R is directly in the equation for the frequency support of the signal. So here is a graph. Left is the frequency response, right is the pulse shape, and therefore different roll-off factors. Roll-off factor of 0 is the ideal Nyquist pulse, and it has the smallest bandwidth. As you can see, it's the rectangle. And if you look in the time domain, it's the one with the biggest side lobes. So the good effect is that it's spectrally efficient. The bad effect is it has very large side lobes. Why are large side lobes bad? Well, if I do have some intersymbol interference, that means that it's probably going to be greater because I have large side lobes. Also, if I just have timing error, so that I'm sampling not at exactly a multiple of the bit time, but someplace off, the larger the side lobe, the larger the error is going to be due to the contribution from other pulses. This just shows you the pulse shapes, what they look like for different roll-off factors. In black is the R equals 0 for rectangular pulses, and then as we go to others. Again, if we're trying to achieve these RC pulse shapes, of course, they have infinite time support, which we cannot deal with in the lab. So, of course, we're going to have to truncate and delay in order to create a pulse that can be transmitted. Here's an example of a pulse that's truncated after 4 side lobes, and it has to introduce a delay of 3 bits in order to realize the shaping filter for these pulse shapes. So I said that we're going to optimally use a match filter at the receiver, and if I want to have the good effects of my received pulse post-filtering looking like an RC form, then what I have to do is use the square root of that frequency response in the transmitter and the square root of that frequency response in the receiver. And when these two are multiplied together, assuming I have a channel which is all pass and perfect, then the ultimate effect of these two filters would give me the cumulative effect of a raised cosine filter. So that is why we see the root raised cosine filter. In order to have the good effects, for instance, robustness to timing and other effects, we would use RRC instead of an RC filter. So it's not really Nyquist, but it's pretty close anyway, and has the effects we're looking for. Okay, just finish up this part of the discussion with the illustration about an NRZ rectangular pulse. This is the spectral density of the pulse, and on the left there's no noise, on the right there is noise, and then if I fix the transmission rate, but instead of using a rectangular pulse, I use instead an RC pulse with a 30% roll-off factor, I can see the new shape here, which is much more spectrally efficient and much better job at rejecting noise. You can see the bandwidth is much smaller. In the case of the NRZ pulse, it's 2 times the transmission rate, and in the case of the 30% roll-off factor, it's 1.3. So it's saving you, and that means that there's less noise getting through on your system as well. So what about noise? We use Nyquist pulses to help us avoid intersymbol interference. Some pulses use more bandwidth than others, and bandwidth may simply not be available. We may want to create a more spectrally efficient, densely packed wavelength WDM system, for instance, practical concerns can lead to ISI even if we are using a Nyquist pulse. So Nyquist pulse doesn't absolutely assure you of ISI, it just helps you. And remember that BER as a function of SNR does not include any ISI effects, but it is something that we can deal with analytically. So if we want to take into effect, for instance, ISI effects, we would have to look to a numerical simulator because it's just not tractable analytically. To close up this topic, talk a little bit about how you go about simulating a sampled additive white Gaussian noise. Additive white Gaussian noise is a random process. N of k is a sample of one of the, at an instant of time of that random process. It is a random variable. This random variable has a Gaussian distribution, it's zero mean, and it has a variance of sigma squared, which we write as I showed you before. So if we consider a random process N of t, which has a typical form that we see here, we'll see on an oscilloscope. When I sample it in my receiver at specific times, these become random variables, each of which is independent of the other, and each of which has a Gaussian, the same Gaussian distribution. So we call that IID, independent and identically distributed random variables. You can show that these are indeed independent, and because of that independence, the autocorrelation function follows directly as being a delta function, and in the frequency domain as being flat in the frequency domain. And that follows directly from the independence. So what happens? So now we know the autocorrelation function and the power spectral density of additive white Gaussian noise, which has infinite frequency response. So what happens when we filter it? Suppose we filter it with an ideal low-pass filter, for instance. If we filter it with a low-pass filter, well, now the power spectral density is a rectangle instead of being flat over all frequencies, and this means that we create colored noise, which means that the noise samples are not necessarily independent from one another, which complicates any simulation greatly. However, it doesn't really, because if we use Nyquist pulses, then we know that at the sampling times, which are when we're interested in the statistics of the samples of the noise, so if we sample it regularly at the bit rate, and these are a Nyquist filter, not necessarily an ideal Nyquist filter, but any Nyquist filter, that indeed the samples will not be correlated, and uncorrelated noise samples which have Gaussian distribution are also independent noise samples. So that means that when we go into the simulator, we can simulate the noise samples as being independent from one another. Okay, then what I'd like to go on to now is a discussion about Monte Carlo techniques in simulations. So suppose I had a coin and I wanted to test if the coin was fair. Is it really a 50% chance of heads or tails? One way that I could test is to run an experiment where I estimate the probability of heads by tossing the coin many times and counting how many times a head appears. This is what is called a Monte Carlo test. Okay, I actually go out and try it and measure how many times. So this gets me an estimate of the probability. Intuitively, I know that if I toss the coin once or twice, it's not going to give me a very good estimate. The more I toss it, the better my estimate of the probability of heads will get. You should run an experiment, many, many times. Just, intuitively that you have to get a informative amount of samples. And what I'd like to talk about now is how do I know how many samples are enough to draw. So we want to take the Monte Carlo technique and apply it to communication systems. So of course that means that I come in, I have some bits at the input, I put them into my system, I have a transmitter, I add some noise to it. I'll put red. This is my input. My random input is the noise. and then I put it through my numerical simulator where I have a channel, some sort of channel response. Then I'll have some receiver I'm testing. I get out something called a decision statistic. I have a decision rule, which makes me pick what bit was sent. So here I have a bit estimate. So this is what my Monte Carlo simulator will do. It will generate bits. It will generate noise samples. It will run them through this numerical simulator where each one of these boxes is implemented numerically. And then, since I'm in a simulator, I know what the real bits were. I know what the bit estimates were. And I just ask the question, was it right? Was the decision I made correct? And if not, I count the errors. And I estimate the bit error rate as being the number of errors divided by the number of trials. So I can use this approach in any numerical simulator, be it MATLAB or OptiSystem, to help me estimate the bit error rate whenever I'm using a system which is non-ideal in some way, where my analytical equations are no longer valid. Sometimes it's just impossible to come up with closed-form solutions in these situations. But so in this way, the numerical simulator is really the only way we have, short of going into the laboratory, to find out what's going on. There are all kinds of non-idealities we might want to check. Non-Gaussian noise, whether we have a nonlinear channel, the effect of finite precision in some of our components in the digital signal processing, quantification noise, phase error, timing error, intersimple interference. There's all kinds of effects that we understand how they're introduced. We can numerically model them, but for which we cannot come up with an analytical expression for the bit error rate. In this simulation, we have to generate two sets of random variables, the data and the noise. And typically what we're going to generate are equiprobable bits in independent Gaussian noise. Of course, sometimes there will be other situations, and a numerical simulation also lets you examine non-Gaussian noises, which can be useful. When we run these simulations, we can run the same experiment many times, and each time we can estimate the bit error rate. So how is it long enough? How do I know that I've run it long enough? Well, if I don't measure any errors, does that mean the bit error rate is 0? Or does it mean that I haven't run enough trials? Well, of course, the only way to know is to run more trials. So you run more trials. Maybe you finally get one error. Can you stop then? Is one error enough to give you a good estimate? Somehow that doesn't feel right. There's too much randomness in when that error actually happened. Is 10 enough? Is 100 enough? How do I know when I've gotten a reasonable estimate? So a reasonable estimate of BER, what's the criteria? And what we often talk about is a stopping criteria. Because if I had infinite simulation power and I just ran a bazillion trials and I got 1,000,000 errors, and I took a 1,000,000 divided by a bazillion, and I'm not sure what that gives, but whatever it gives me is the bit error rate. Okay, I had 1,000,000 errors. I probably got a pretty good estimate. But what happens if I don't have infinite computing time and I want to know, when to give up or when is good enough? And to do that, I typically use not deciding ahead of time how many trials to run, but to run trials until some criteria is met, until I can stop. And the stopping criteria is usually something like 10 to 100 errors is a typical stopping criteria in a bit error rate Monte Carlo simulation. Also, I want to mention that I call these numerical simulations, but actually when you go in the laboratory and you want to measure bit error rate, you're just running the same system, but this time with hardware instead of with software. And actually you're also estimating bit error rate. So if you're running a system and you want to know how many errors do I need to know that I have run my BERT long enough to get a good estimate of the bit error rate, or if I'm offline processing a coherent detection system, how do I know that I have captured enough data to make a reliable estimate of the bit error rate? It comes to the same stopping criteria. It's the same mathematics. And the good rule of thumb is between 10 and 100. 100 is better, but if you really, really can't get to 100, then 10 will give you, something that's reasonable. So remember, applies to BERT, bit error rate tester measurements, and to coherent detection offline processing, and to numerical simulations. Okay, so just remember that we do have recourse to theoretical curves, and that, like the homework is trying to show you, you should, when you run a Monte Carlo simulation, always be validating regimes of operation for which equations exist and can check and see if your Monte Carlo is accurate. If I was God and I knew what the true bit error rate was known, then I would have a pretty good idea of how many trials were needed. Right? If I know that the bit error rate is about 10 to the minus 3, then if I did 10 to the 6 trials would be, way more than I need. If you knew the bit error rate, you would know how many trials to run. But of course, you're running these trials because you don't know the bit error rate, so it's not really useful, except that I'll try and explain where this rule of thumb of 10 to 100 counts comes from. And it comes from posing the problem when the true bit error rate is known. Paper by Michel Joachim, about analysis of Monte Carlo confidence intervals. And so what you'll see in that paper is these curves. If you look at the curves here, what we're plotting is that, and the x-axis are the total number of bits observed, so it's the number of trials in your system. And on the left is the bit error rate that you're going to get as an estimate when you do that many trials. And these curves are generated when the true probability of error, the true BER, is equal to 10 to the minus k. So here we have the true one is how we're centering our plot in our calculation. And k doesn't have to be an integer, but whatever the bit error rate is, these curves, and I won't go into the derivation of the curves, it's in the paper if you're interested, but what we see labeled here are different confidence intervals. So if I look, for instance, at the curves for 90% confidence intervals, this gives you both the maximum and the minimum that your estimates are going to most likely fall between, or fall between with 90% likelihood. So if I were to do 10 to the k simulations, and the probability of error was 10 to the minus k, then these would be the bounds that with 90% probability, my estimate would fall somewhere in that range. And so let's take another one. Let's suppose that I did 10 times as many trials as the inverse of the probability of error. So if I take this example, then this is 10 times 1 over the true probability of error. And if I put a line here, more or less, okay, and then I looked at where this intersected, let's say the 95% curves. And don't draw very straight lines, but trust me. Oops. This is happening at about 2 times PE, it's this point there, and about 0.5 times PE. So that means that for 95% confidence that my estimate will be within a factor of 2 of the true value, I have to run about 10 times more trials than the inverse of the true probability. Of course, the problem is that we don't know the true probability. Obviously, that's why we're trying to estimate it. Therefore, I can't really compute how many trials I need. If I knew, I could compute it. So now we think about one approach we could use is to count errors. If I measured 10 errors, then maybe I have run about 10 times 1 over PE, right? If I ran 10 times, then the expected number of errors would be equal to 10. So suppose I count 10 errors. Well, it doesn't mean that I've actually run exactly 10 times 1 over PE, but it means I'm probably pretty close to this confidence interval. And that's why we say that 10 is probably enough to get within an order of 2. But there's enough uncertainty in the stopping criteria because maybe for some sequences, for some reason, I get a noise burst and all the errors occur early, and then my estimate will actually be very different because it's not exactly equal to the expectation over infinite runs. Say that there's more error involved in this prediction, which is based on when you know what the true bit error rate is. So it's not as good as 95%, but it gives you still at least some quantitative feel for how much better you're doing when you're using this number. So this is where you get this rule of thumb. And then I wanted to just mention that there is in MATLAB a package called BER Tools. And BER Tools is specifically designed to help you with this quandary about when should I stop, how many trials should I run. So MATLAB in this package, it manages sweeps of BER. So you want to get some curve, you want to vary SNR, you want to vary some parameter and see how the bit error rate changes with this parameter. So you want to sweep through it. And there'll be some regions where your BER curve could typically span from 10 to the minus 2 to 10 to the minus 6. This would be a typical span for a bit error rate. Or maybe you want to have a good computer and you want to go 10 to the minus 8 or something. But anyway, you're going through many decades of bit error rate. And you don't know in the beginning where you are or how many it's going to take. So what Bit Error Rate Tools does is it just helps you sort of manage these decisions about how to do it. And what it does is it starts with a block size. And it's a block size that corresponds to sort of the smallest set of bits to be tested. So you say, I'm going to try 10,000 bits at a time. I'm going to run 10,000 bits, and I'm going to see if I get any errors. And if I don't get any errors, well, I'll start iterating. Iterates to get more errors. So if you choose your block size too large, you're going to do a whole lot of computing power to measure 10 to the minus 2 when you don't need to. You're going to measure 100th of those are an error, and so if the block size is really big, then you're getting many more error counts than you need to get a good estimate of that bit error rate. But if you would choose it too small, then you're doing this sort of for loop, which is really, really inefficient in MATLAB especially, where you're just running the routine too often. There are too many iterations, and it would be more efficient to have a larger block size. All BERTool does is just gives you an easy forum for making these decisions and changing them and managing them. And you can always have an absolute stopping criteria, which means, this much time goes by, just stop my simulation. So the other day in Professor Yan's class, you talked about using OptiSystem, but it actually used BERT tools to handle the calculation done by OptiSystem. So BERT tools managed this decision about what size of block to generate in OptiSystem and how to do the sweeping and the iterating and to make sure that we've counted enough errors. So that this management of the Monte Carlo techniques was moved outside of OptiSim. And I didn't do it for the homework. I probably was to include BERT tools in the simulation of the Monte Carlo. The idea, I just want to let you know that this tool exists and that you'll probably be seeing it elsewhere in the class. But it's all related to this theory about what is a reasonable number of errors. But you can always tweak that even using BERT tools, whether you want to count these 10 errors, if you're willing to go to 100 or whatever you want to step through. I'd like to go on and just talk about the Windsor paper and the homework. This is the paper I'm referring to where they're looking for optimum filter bandwidths for NRZ receivers. And in this assignment, they're looking at receivers that have a fixed filter. We know that match filters are the best strategy. But they will truly maximize SNR and give you the maximum a posteriori estimate of the bit. So they're good in that respect, but they're bad in another respect is that they're channel dependent. Because they really should be matched to the transmit pulse shape, whichever one we use. Okay, I'm going to do it in the frequency domain. You'll do it in the frequency domain, times the channel response. And this is what the match filter should be matched to. And sometimes I just don't know the channel. And ignoring the channel is not at all a low pass, so all pass. So putting in all pass is not a good idea. So often match filter is not necessarily practical. And instead what we do is a common simplification is to just use a fixed low pass filter. And then the question is posed, well, what bandwidth should I use for the fixed low-pass filter? And there are some rules of thumb in certain additive white Gaussian channels. What would be a reasonable bandwidth for the low-pass filter? And in some cases, there's actually a standard. So in this paper, they talk about the Sonnet standard. And the Sonnet standard was to use a 0.75 R bandwidth fourth order Bessel function. In the end, what you're dealing with is then you have your pulse shape. We'll go time domain now. Convolved with your channel response and pulse response. Compulsed with this sort of low pass filter, which you're using because the standard says so, or because you really don't know what to use, and so that's convenient. What is the effect of this analog filter? So that's the question that's being asked. If the 0.75 R worked in systems which were maybe WDM multiplex but very, very widely spaced, the signal width was much smaller than the width of the optical bandwidth, then this rule of thumb that became the standard for Sonnet would be fine. But new systems where we suddenly want to be more spectrally efficient, and in the paper they talk about trying to become more dense WDM, which means that you're doing the electrical bandwidth and the optical bandwidth are getting closer in value, which has an impact on what might be the best strategy for that low-pass filter. The kinds of optical filter shapes were changing. This paper was dated, I think, in 2001. And so technologies were changing on filter shapes. So they had some with much sharper roll-offs, which would facilitate the denser values. Yes, I had a question? Okay, so the question is about, is the channel static, and can an estimate of once be enough? And it all depends on the system you're using, what the situation is. Let's take wireless systems. In wireless systems, you would assume that the channel was changing in time. It's quite the norm. And you would run an adaptive filter, and you would update it periodically. Certainly, depending on what kind of system you're using in optics, there may be some effects that are changing. Maybe it's temperature effects. Maybe it's not. They're slow effects. Maybe there are other things that are changing in the channel. Maybe it's a reconfigurable network and things that could be changing drastically on the channel. It just depends. But the problem in optics is that the speeds are so high that running an adaptive filter is prohibitively expensive. And maybe with coherent detection systems this is less the case, and maybe we'll see this more, but it's still, there are already fixed effects that would have to be treated in DSP, and now getting time-varying ones would also be difficult. So maybe it's a compromise between what's actually going on in the system. And like I said, it just depends. It depends which channel you're talking about, and what you're willing to pay for in terms of processing. So in this paper in particular, it's an on-off keyed system, one that is going at the highest electrical bit rates that they could at the time, and doing any sort of adaptive version would be impractical in cost. And so they're looking for a very low-cost solution, which would be with a fixed filter. In this paper, here, the system that they simulated, and you can see it's very similar to the system that you'll be simulating in the homework. They're generating different pulse shapes. Here, they're doing, I think it's called a cosine squared, and this is what they call a practical NRZ. So, even the equipment cannot produce a perfect rectangular, that there's a pulse, that there are rise times involved in the equipment, and so this is sort of using a reasonable pulse shape. So they're doing pulse shaping before they transmit. Then they have an EDFA, where it introduces spontaneous emission, goes through an optical filter with a certain bandwidth, and they test different filter shapes. So they're looking at Fabry-Perot, and they're contrasting with Fabry-Perot grading filter shapes to see what impact that might have on your decision on what kind of low-pass filter you would use. And they use two kinds of low-pass filters. One is a RC circuit, a simple low-pass filter, and the other one is a Bessel. And they go and they put it through a threshold detector and count errors. So this was a good example of research where it would be very difficult to sweep through all kinds of filters in the lab. You would have to buy different filter widths, different precisions. It's something that's much more amenable to doing in simulation. So the issues that you're dealing with in the homework are similar to the issues that these researchers were dealing with in building a simulator for this system. That's all I had about this, just to motivate you to say that if you were interested, you could probably take our homework and actually just change the parameters if you wanted to create this. Also, that although this example is with on-off keying, filtering effects also has a large impact in coherent systems. Baud rates are being pushed, and they reach the limit of the frequency response of the components. It creates impairments. We try to get BSP to help. But certainly to achieve what we call Nyquist packing of the frequency, to get frequencies as dense as possible, one way is to use pulse shaping. so the Nyquist discussion is relevant, especially in the coherent detection systems that we're looking at today.